We'll now look at the fundamental group of an arbitrary graph, or with only the condition it's connected. Okay, the picture I've drawn here is a finite graph, but everything we say is going to be true independent of cardinality of anything that we want, except for one statement we'll see finally about cardinality itself. Okay, so how do we calculate the fundamental group of a graph? We know how to handle trees. Trees are contractible. Well, any graph, so here's an important proposition. I'll draw the picture here. So sitting inside a graph like this, I can look at a bunch of edges this way. Maybe this was a bit misleading because the purple edges form a somewhat simpler graph than is typical. But you see, this is a tree. That purple thing is a tree. And it contains all the vertices of the graph. Okay. And so the following proposition is not hard. The proposition is gamma has a maximal tree okay, and B vertices of T is vertices of gamma. Okay, actually it would be perfectly adequate to say gamma has a tree whose vertices are the same as gamma, or you can say that gamma is a maximal tree and maximal trees have this additional property, which is the way we have put it. The reason is you can just start with a point x0, our favorite point, that's a tree, and keep expanding. And if it's finite, you use induction, and if it's infinite, you use Zon's lemma or something like that to claim that you get a maximal tree using the fact that increasing union of trees is trees. The definition of the tree is a tree. Okay, so I'm not going to give more details of that. How about the second one? Well, you see the graph is connected. So if I had a partial tree, maybe I only had this much. Okay, then it does not contain a vertex. And maybe I was unlucky and I found well, that was too big. I found this vertex that is not contained. Well, I can find a path from that to x0, and perhaps I took this path. Well, say a reduced path. Well, this path for a while it's going to be inside the tree. Then it has to exit the tree, and the first edge where it exits the tree is something adjacent to the tree but not contained in it. Okay, and well, you could be unlucky and the first edge could be a loop, but in that case simply delete that. So there will be a non-edge loop and make a shorter path. So take not only a reduced but a shortest path to this vertex. The first edge outside can be added to the tree and you'll still get a tree. Okay, so I have not written down any of the details. This is an exercise. It's purely combinatorial. There is no topology, and it's not. It follows the line that I have said. Okay, so how do we have the statement here? Okay, so there are certain edges which are in the tree and certain edges which are not in the tree. Okay, in this case there is a pair of edges even bar here which are with opposite orientation, and another e2 bar. Okay, and I'm going to call this eta 1. So the disadvantage of our combinatorial model that we have chosen, so I'll emphasize this is a set. So eta 3 is E3 bar is that what we geometrically think of an edge is two oriented edges. So let's simply introduce the terminology unoriented edge. Eta is a pair of edges and of the form E and E bar. Okay, so this is geometrically an edge. So what do we have here? So the purple part is, well, we have many colors here, but ignore everything except the purple and the black. So we have this, and this, three edges that are not in the tree. Okay, and well, if you had a tree, the fundamental group will be trivial. You can think when I add such an edge, I have kind of added a loop because I can go within the tree between the two endpoints as well as along the edge. Here I've literally added a loop. So each guy is a loop. And the theorem, so let me write down definitions. So let S be the unoriented edges not in T. Okay, so we're looking at edges, and the theorem here is pi 1 of the graph with the even base point is what we denoted this, which is the free group generated by S. Okay. We are actually going to prove it's a free product, so we'll use the relation between free products and free groups earlier. So we are going to use Van Kampen's theorem, of course. So the proof is by Van Kampen theorem. With x0 equals, well, I would like to take it to be the tree itself, but in fact I have to take a neighborhood of the tree. So frequently in Van Kampen's theorem, when we apply, the tree itself is not going to be open, but there's a small neighborhood of that which deformation retracts onto the tree. In this case it is this region. So if you wish, I will just add the little yellow portion which is almost invisible. That's terrible because I can't see my yellow pointer. Sorry. Okay, maybe yellow is just too silly. Let's add a brown portion. So we add this little brown portion here to the tree, and we get a neighborhood of the tree. That neighborhood deformation retracts onto the tree itself, and various intersections also will. Okay, so I'm going to pretend x0 is actually the tree itself, and similarly for each edge in S, for eta is E bar in S. What do? I have paths. Okay, so well, there are a couple of cases, of course, but if I take a typical edge here, okay, then I look at the initial vertex of this edge E, and I look at terminal vertex of E. Okay, and then we had paths which I call theta I of E. So we'll simply call the space XE is theta I of E, the initial vertex, union theta tau of E. Okay, so there's a path to the initial vertex, there's a path to the terminal vertex. In the case of this guy, it's this path to the initial vertex within the tree. Okay, so I'm talking about the edge here now. So I have an initial path, and then I have a path within the tree to the terminal vertex, which in this case goes this way. This is the unique path. Remember, there is a unique path. I don't have a choice. And union the edge itself. Actually, I have to take a neighborhood of these. So I have these things. Okay, so what happens to this space? Okay, in this case, I have a single path and this one. So now what we note is, first of all, X is x0 union the big union of E in S, or more precisely I should say E bar in S of XE, because every edge is contained there and the tree is contained here, every vertex is already contained here, and these are open sets because I've taken these little neighborhoods, but all the intersections and the sets themselves deformation retract. I mean the neighborhoods of all the intersections of the neighborhoods as well as the neighborhoods themselves deformation retract to the respective sets and their intersections. So we can pretend that the spaces we took were the tree as well as these, which we shall do. Okay, so what do we know of the fundamental group of these? Okay, so that we will see next. So first of all, pi 1 of x0 with the base point x0 is trivial. Okay, and how about pi 1 of xe with the base x0? Now in our examples, xe was homeomorphic to a tail and a loop, right? Whatever it is, whichever case we had, but there is another possibility that it is just a circle. Okay, this follows from properties of trees. As I said, you have one path and you have another path. So basically you have two endpoints of the edge and you have two paths, and the nature of two paths is that they overlap for a while, but once they diverge they never converge again, otherwise you would get a loop. If they overlap not at all, you diverge straight away, and in which case when you connect it with this you get a circle, otherwise you get these. So in this deformation retracts, so this is homotopy equivalent to of course a circle, and the second case is a circle. So we know that the fundamental group is Z. Hence pi 1 of mod gamma comma e is x0. Well, this is the trivial group star. Okay, so the trivial group star anything, by the way, star something or the other. So I'll make a remark here. The free product of the trivial group with G is G, whatever the group is. So this part can be ignored, and it's the S in S. Well, I've called it little s, it doesn't matter, because whatever the group is Z. Okay, and remember we saw that the free product of these is just the free group. Sorry, it's denoted this way. So this is done. So we know the fundamental group of each graph. So here's an addendum. Okay. So for a tree, for a finite tree, so what happens if our graph is finite? For a finite tree, we know that vertices minus edges is 1 always. Well, you can see for sanity in the case of a single vertex, which is a tree, then vertices is 1 and edges is 0. And if I took an arbitrary tree like this, okay, a fairly easy combinatorial argument will tell you that it has a terminal vertex, provided it is finite. Okay, namely a vertex which has only one edge incident to it. Okay, that is because you keep expanding, and so you look at this vertex and you look at the adjacent ones. If any of them is terminal, you're done. Otherwise, you can continue expanding, and you either come back to a previous vertex, in which case you'll get a loop which gives you a contradiction, or you stop somewhere and that will give you a terminal vertex. Okay, so any tree has a finite tree has a terminal vertex, and if I get rid of this vertex and this edge, then I end up with one less vertex and one less edge. And so by induction, that has v minus e is 1, and v minus e has not changed by this deletion. Okay, so for a finite tree, this thing is 1. So corollary, or rather addendum, so hence if mod v, and so if the number of vertices and number of edges is less than infinity, well, how many extra edges do you have? Okay, so I can rewrite this as saying edges minus vertices plus 1 equals 0. Okay, I took it to the other side. E minus v plus 1 equals 0. Okay, and now we took a maximal tree, it has all the vertices, and we want the extra edges. Okay, so what we say is that mod S, this is called the rank of the free group. Mod S is going to be equal to E, well, strictly speaking, this I should say cardinality here and cardinality here as well. So mod E minus mod V, mod of, well, okay, plus 1. You may have spotted there's a problem here. So I'll just call this E hat or something like that, because our edges came in pairs. So this is not the cardinality of the set E. So this is number of unoriented edges, number of geometric edges. So this is nice. So we not only know it's a free group, we know it's how many generators it has. Okay. Now it's elementary to see that if you have two free groups on the same number of generators, then they're isomorphic. Namely, use the universal property and map the generators bijectively. The converse is also true. It's not so easy. Easiest way is to Abelianize, and notice that you have z to the n and z to the m, and so if groups are isomorphic, so are their Abelianizations. So what I'm saying, so if Fn, which is the free group on n generators, is isomorphic to Fm, this implies that z to the n is isomorphic to the z to the m, and you can use structure of abelian groups. But if you prefer abstraction to the structure of abelian groups, which is a little bit of hard work, you tensor with Q, and you get Q to the n is isomorphic to Q to the m, and then you have the more elementary linear algebra fact, or even R, that the dimension of a vector space is well defined. So what I'm saying here is that if I take free groups on different numbers of generators, they are not isomorphic. So we know which free group we have got. It's completely determined by the number of generators up to isomorphism, and that is determined in the case of finite graphs by this. You look at the number of geometric edges, unoriented edges, minus vertices, add 1, and that will tell you which free group we have.